I'm not going to be tempted to make this now. Sorry. Okay. If you bring me a builder's hat, I will. No. Okay, good. So that's clear. This is just the open game. And so why do we keep the function, the payoff function as a parameter here is exactly to be compositional. That is kind of the crucial bit, I guess, of open games. It's not just a different representation of this. The crucial idea is that if we keep this function here, the equilibrium function, as a higher order function, we can compose things in a nicer way.
I wonder, isn't the co-utility usually singleton here?
A singleton? No, no, no. So the co-utility, so just to remind ourselves.
R to R.
Because they're about to iterate it.
Yeah.
Yeah, if you, Clemens will probably say this, but in order for the iteration to type check,
Sure.
you need to have the co-utility and the utility have the
That's
same.
true.
Wait, is this the right type of the co-utility?
Prisoner's dilemma, you would not have.
You don't have to, but then you could.
Sorry, what was the question?
The question was, why is the type of the utility the co-utility the same?
If you were modeling a single shot dilemma, you would have trivial.
Sorry. Good point. So in general, it doesn't matter. But now if you want to plug things together, I mean, doesn't matter is the wrong way. In general, we are more general. Another classic for YouTube, sorry. Okay. Sorry. So just as a, so what we, okay, I somehow, here there should be now a slide. What are we going to do exactly? We're taking this game as an example, and we're going to iterate it at the end. And so why is it interesting to look at the prisoner's dilemma iterated? Because if you look at the infinite iteration of the prisoner's dilemma, then suddenly cooperate can become a valid strategy. I mean, it's not really cooperate. The strategy is rather that in each round the players are cooperating for some reason. Because, and what is the reason? Because there is a threat that if you don't cooperate, then for infinity you will be punished, basically. So the point is, if there's only one round and you defect, you go away, and what else can the other guy do, right? But if you're in the infinite game and you deviate from the strategy, then the other player can punish you until the end of time, which is, it's almost like a religious example. Okay. Anyway, good. So that's and we are going to do this construction of iterating. So now we go to do this construction. We are always in the framework of category theory to do this. I mean, if I write an arrow here, that means something in a second, namely now here. Namely, so this is just a brief side remark. So we have this category. We introduce. Let me backtrack. In general, I don't think so. Open games are by now quite established. The question is still a bit like, what is the category of open games, right? And what is the problem about the category of open games is what are the right morphisms?
You're talking about the category where the objects are open games.
Yes. So this category is not so. As a first simpler category, we have the following here. It's the category of open games, where we have just pairs of sets as objects, and the arrows in this category are, in fact, the open games.
And the homes are proper classes.
The homes?
You just parameterized by an arbitrary set, so they can get big.
Yeah, it's okay.
Well, I don't know why sigma sort of is there at all, to be honest. It seems really what you want is a subset of a certain collection of functions which are defined by x, r, y, and s. The fact that maybe r isn't even involved. But adding sigma, it makes things into a proper class, which seems a bit funky.
Yeah. I think we could, for example, just restrict ourselves to finite sets. Sigma, I mean, if you just think of sigma as the strategies, you definitely could give it an upper bound, I would say. Yeah.
At most continuum or something like that.
Yeah, it seems to be better for
Yeah, so I also have to say that this kind of errors now won't take much of space in this talk, but I wanted to mention it because there's one construction which we're going to use in a second. So this is the category, and on this category we can define a functor on this category. And so what does this functor do? It introduces some kind of dependency or some extra set A of previous choices, which we will see in a second. Because what we have to do for the iterated game, we have to say the iterated game is one round of the game followed by the iterated game. And to glue this properly together, we need something like, once we play the first round, the second round depends in a way on the first round. So, and this dependency here is given by this set A. Later on, it will be just the moves from the first round. I see. Okay, good. So suppose we have an open game, an arbitrary. We can just define this game, the A arrow game, A arrow H, which just says, okay, instead of the states X, I also have information about an element in A, which could be the move produced by the first round, basically. And then we have strategies are now not anymore just the strategies before, but they're functions depending on where we are. And then we get again an A and a move in the game. And so how does the play function work? So if we are in a state A, X, and we have a strategy, well, what could be more natural than just take this function, apply it to this A, then we have a strategy in the original game, and then we can just apply the play function to this strategy. So note here, everywhere, I have states X, which could go out, and I was considering moving them out, but I thought it gives the wrong impression saying that, I mean, it doesn't really matter whether there are states here or not, so that's why I wanted to keep them in. So this is the play function. The co-utility function, I'm now not going to discuss because I'm probably just confusing myself. And the co-utility in my talk is the identity. And then we have the equilibrium function. And this is one of the important bits here. That's why I called this slide subgame perfection as a functor, which is a bit of overstating it. But so this operator is exactly kind of ensuring then in the construction that we're doing that the equilibrium we get will be what's called subgame perfect equilibrium. So I mentioned the Nash equilibrium before in the one-round game. In general, in the infinite game, we are more interested in what's called subgame perfection, which means that basically all your moves have to be optimal in some way. But also if somebody deviates, still your strategy from that point onwards again has to be optimal. So it's not enough just to make sure that you're on one path optimal, but you need to be optimal no matter whether somebody deviates or not. And so this is exactly given here by this for all quantifier. So what does this say? So we say a strategy here is an equilibrium for this game if for all possible options, if I get the corresponding strategy, it has to be an equilibrium for this H game, where we say that, where we however now register in the payoff function that we had this, that we are kind of taking this path. So, yeah, so I made this point here. This is the main point of the whole slide, to be honest. Well, we need this construction to do the iteration, but we also, crucially, we have to have here the for all quantifier because we're interested in subgame perfection. So maybe if somebody is interested in something else, who knows whether one can do something about it. Now, yes?
This equilibrium function looks very much like the one deviation principle.
Yes.
Is that
Yeah. The answer is
I think that's slightly separate. See later on that in the iterated game, by definition, in this treatment, every single stage must soon as you take this finite algebra approach, or even as soon as you take a compositional approach, it has to be built from blocks if it's compositional. We'll talk about some of the stuff
Yes.
since.
Okay, and the only lemma I wanted to mention about this thing is that it's in fact a functor on this category. And that's also the only reason why I briefly mentioned this category, to be honest. It won't be taking much more space here. I think Neil once thought that it would be a comonad.
Yeah, I thought it should be something else.
But I think there was a good reason for why it wasn't a comonad, although I don't recall now.
The funny thing is, if you take this functor with my morphisms, I think it's a monad. But with your morphisms, which you need to combine with this, it's not. It's very hard.
Okay. Now, what we are now looking to do the construction itself. So the construction, always recall, is iterating a game, and the construction mathematically will be the construction of a final coalgebra. Although construction is a bit rich. I mean, it's a existence proof in a way. Okay, so we have this category of two open, which could be, yeah. So two open is the following category. So now what we're doing is, so the objects are now the open games, and the morphisms are open game morphisms. So we basically go one step higher up. So here we had these objects and these arrows. Now our objects are these arrows, and we have arrows between the arrows. As always happens, right? Okay, so because now we are about to approach this iteration, what we do is, first of all, to make the construction simpler, we assume that we are having a state-free game, like the prisoner's dilemma. And secondly, the co-utility and the utility have the same. So as you know, I mean, as you saw before, this is perfectly fine with the prisoner's dilemma. Now, what's the morphisms between games? So suppose we have two open games written here. A morphism is a pair of functions. So what we have to do somehow, okay, what do we have? We have moves and we have strategies. We have to link them up somehow. So we have basically a function from the moves from the one play to the other game, and strategies from G to strategy to G prime. And then, well, you look at it, and then after a while, you realize what it should be somehow. So if you take a strategy in the original game and play a move, and then map it to the other game, it should have the same effect as first taking the strategy, mapping it to the other game, and then moving. So this is the more obvious condition. The other one is about equilibria. So basically, suppose I have a strategy in my original game, and I have a paid function in the G prime game, then I want that if I'm in the equilibrium for the payoff that I'm getting here by post-composing with alpha y, so that is this guy here, then basically I need to be in equilibrium. The image under this function has to be in equilibrium in G prime. Is there a good motivation beyond that the types fit nicely together?
I think it's appropriate to say that there's a number of different possibilities.
Yes.
And in fact, as Jules mentioned, he actually uses a different notion for a particular purpose. But beyond that, there are still quite a few different possibilities. The most general one is based upon lenses, and it naturally leads to this kind of approach. But it's complex because when you have the utility, the equilibrium, it's a higher order function. So then you've got functions between higher order functions, which is covariance. That's why there's lots of possibilities. It's not entirely trivial.
Yes.
The second condition is preserves Nash equilibrium. It says that it maps Nash equilibrium to Nash equilibrium, which is intuitive enough, I guess.
Yeah, it's very intuitive that it maps Nash equilibria to Nash equilibria. It's okay. It's a bit less immediate that you have to do that trick to the Nash equilibrium with respect to which payoff, basically. That's
That's contravariance.
yeah. So that contravariance, I was mainly now worried, not worried, but looking for a good explanation for that contravariance. It feels very natural. I just don't know how to give a more rigorous argument right now. So now we're reaching the point of the talk where one more pass wouldn't have been bad. But anyway, so what I wanted to point out now is that, okay, what do we want? What do we know immediately if we see these morphisms about iteration? And so I'm just now telling you this without you knowing already. So I mentioned it in words. So the iterated game, somehow, the infinitely iterated game, should satisfy this fixed point equation, so to speak. So what is the equation saying? It says the infinite iteration of a game should be the same, should be basically playing the one-round game and then followed again by the infinitely iteration. But now it won't be just the infinite iteration, because where would you plug the moves basically here? So if you draw this, you will see if you don't have the y arrow here, this composition is not well typed, because this produces some y, and this will be in fact a state-free game, and therefore you can't plug them together. So that's exactly why we need this construction from the previous slide. We need to be able to glue these two together. So, and so intuitively, this is very, very natural, right? So you just say the infinite iteration is the same as I play one round, and then I take the result and continue with this, the infinite iteration. So once we know this, so we should also think, what do we mean here? If we write an isomorphism here, now we mean really isomorphism in the category we just defined. And therefore, if I want to somehow achieve this, and if you look at the definition of morphisms I showed you previously, that means immediately we will get this isomorphism will consist of two isomorphisms. The first one of this type, so z to y times z, where z is now just the set of moves of the iterated game. And then we have the other one, which takes the strategies of the iterated game and yes, strategies of the iterated game, and produces a strategy of this game. A strategy of the composition consists of a strategy for this game and a strategy for this game, which is this. So all in all, once you know that you want to have such an isomorphism, I mean, and that isomorphism should be there because it is there in, well, I wouldn't say, conceptually it has to be there. With our definition of morphism, we get these two components. And so what, yes. Now, however, I don't want any fixed point here, but I want to have the greatest fixed point, because we know that infinite iteration usually is represented by a greatest fixed point. And so this is hand waving right now. I'm just trying to give you the intuition how we come up with the definition, basically. The point is now that because we want the greatest fixed point, we kind of want the greatest fixed point of these two, which are final coalgebras. And they are very well known. And I think I have them on slides. I mean, you see this one. Intuitively, what does such a thing do? I mean, these things, these arrows here live in set, right? So this thing produces something of type y and then continues. So intuitively, this is a machine which somehow produces an infinite sequence of y's, which is very natural in that setting, because an infinite sequence of y's is exactly like a move in the infinitely iterated game. And this thing here, so what does this do? Well, it somehow gets a move and then moves on and outputs in each state a move in the single round game. So you should think of this as something that produces in each state a strategy for the single round that we are just playing. And then depending on what was actually played, we continue in the strategy. So let me just mention this as a fact here. So this construction here is again functorial in the appropriate category. So if we have two open games G and H, then this mapping FG of H that produces exactly this game here is again a functor, but this time on the category 2 open. So now let me just briefly describe this final, let me go back again. What is really essential for the final coalgebra we're describing are the two final coalgebras for the, basically for these set functors. So what are these final coalgebras? So the one final coalgebra, which corresponds to this alpha sigma, is the following. So you remember alpha sigma was exactly this, had this type producing a strategy or moving to the next state. So I'm writing here that functor d of y is sigma, which says, okay, y is the way I can go to the next state, and sigma is just, sigma corresponds to the sigma g on the previous slide. And the functor itself on morphisms is just defined accordingly. I mean, so if you have a map from x to z, what it would do is, well, you keep basically these outputs, so to speak, they keep constant. And if I want to have if I start with y to x and I have a map from x to z, I can just postcompone the f to get something from y to z. So this is a well-known functor. In fact, this is like the prime example of coalgebras. That's why I wanted to put it, because a lot of coalgebraic theory was developed or is developed around this functor, because it's about finite automata, and finite automata are, well, everywhere in computer science. So these coalgebras are automata. Originally had finite automata, but they're not necessarily finite, that read finite words in over y and outputs element in sigma. And then accordingly, with this image in mind, I can describe the final coalgebra describes you the behavior of, like, it gives you a canonical representation of the behavior of such a coalgebra. This can be described now as follows. I have it here. So its functions from y star to sigma are the states, because the behaviors of these coalgebras are functions from y star to sigma. And now to turn this into a coalgebra of the right type, I have these two functions now and later. And now, what does now do? Well, now basically just outputs the function applied to the empty word. It's like what happens now according to this function. And what happens later is basically where later f is a function that reads the y first. This is this thing here. And then is again a function from y star to sigma. So this is what's called the y derivative in a sense. So you read one letter, and now you move to the function where we keep in mind that whatever we put as an argument, we prepend this letter that we just read.
Just a question, could you also learn this coalgebra? So what would you learn that if you let the player learn it, play optimally?
I mean, I can learn this coalgebra, but I don't have a player learning it, so the answer is yes and no, basically. I know ways of learning this using algorithms, but I don't have the picture of a player learning this thing on the fly during a game or something like this,
Yeah.
which would be the useful thing.
Yeah. Why do you don't have a picture? What do you mean?
I mean, meaning this is like something more statical. I mean, you know that you want to learn a regular language, and then you can learn by applying some tests exactly the automaton for the language that you're trying to learn. But I'm not sure whether this can be, so for example, in a game, what you can't do is, right, you can't play like 10 rounds and say, okay, now I know enough, let me go back to the beginning and then run a different match. I mean, basically, if you can always rerun the match from the beginning, then it should be possible. If you're kind of in the middle of the game and you just do observations as they come, then I'm less sure how it works. I mean, with what I know, I'm sure that there are people who can learn this. But you see, there's a difference, right? I mean, yeah. That could have been the other talk I could have given, right? But anyway, I didn't want it specifically because I didn't want to give you the wrong impression that I can learn everything, even though learning means something different in this sense. Yes, so we could learn this, to keep a long story short. Let's discuss this. I mean, there's something we...
Yeah, okay, so this is a topic for research for sure.
Yeah.
Basically, I know only the non-sexy part of learning. Which is also, no, okay. Which is called automata learning. Basically, there will be a workshop next week. But I'm not going to be there, but I mean, it will be interesting. It's about automata learning. But it's not so much about that kind of deep learning or something like this. Anyway, I'm happy to...
We're going to talk about that later.
To discuss this later, indeed. Okay. So then we have the other thing which we had was this function from z to y times z. And so the final coalgebra here is just, as I said, streams over y. So these are the infinite sequences of y's. What turns this into a coalgebra is the canonical structure is we can chop off the head to see what's the first element, and then we get the rest. So that is the stream coalgebra. And now, as I said before, we want to kind of, before, I mean here, we have basically these coalgebras as part of the iterated game because of this kind of high-level observations I made here. So therefore, it shows up now when we define the omega iteration. So now we want to, so we pick this game, we want to define the omega iteration of this game. So first of all, what are the strategies? Well, the strategies are the final coalgebra of that one functor, which we had, meaning now the strategies here are, in fact, just function from y star to sigma g. I mean, if you go back to the functor, this is exactly the final coalgebra, given what I told you. And then the play function for this thing, given such a thing, can be defined using the final coalgebra for the other functor. Because if we are having a strategy here, we can turn this into a coalgebra of the right type. And then, okay, so in all my talk, I'm mentioning final coalgebra. Does anybody know what that means, in fact? So here we see the first proper finality diagram. So what, okay, Jules knows what it means, so let's go further. So what does it mean? That this is the final coalgebra. It means that for any coalgebra of the same type, so this is the y times x coalgebra, this is the y times x coalgebra, this is the final one. For any such thing, I get a unique coalgebra morphism into the final coalgebra. Now, what does coalgebra morphism mean? It means that, well, if I apply that y times functor to this function, I get this square, and this square has to commute. So do we want to know how this works? So if I have such a strategy, basically, how do I get such a thing? Well, in the first component, what I just do is I apply the now function, which tells me what I should do now. And then I use the play function for the one-round game to get, in fact, a move. And then to go to the next strategy, what I do is basically I take sorry, I hope I did this correct. Yeah, so this is the function which takes such an x, goes to the later of x, which remember takes a y and should produce another x. And so how do we do that? Well, we're just playing that current strategy again. Actually, so we did we did this just as a definition in the paper. I just put that relatively simple diagram exactly to show you what finality somehow does. It allows you to define functions into the final coalgebra in this way. Well, that's one use of. So this was, sorry, what did we define now? We defined the strategies. We defined the play function. Did I forget something? So we need the equilibrium, right? I hope I didn't forget anything else, because otherwise I'm in trouble. So the equilibrium is now the complicated thing. And the equilibrium should now exactly do what Philip also mentioned, like this kind of idea that this one-shot deviation principle iteratedly ad infinitum, so to speak. Okay, so what we have, in order to define the equilibrium for this game, which has this type, it's like a predicate over strategies, and it takes a utility function. We define an operator on this set. So this operator phi is just a monotone operator taking these kind of index predicates over strategies to index predicates over strategies. And the equilibrium function will be basically the greatest fixed point of this monotone operator. So when is now a strategy in basically in phi applied to some predicate of k? So this is an index predicate. Phi applied to it is again an index predicate. And then here we specify the index to get just the predicate. Now you want to say when sigma is in here. So when is it in here? Well, first of all, the now of sigma. So you should think of that as the condition that we want to maintain in all rounds, so to speak. So what this says is that now of sigma, which is the thing which we want to do right now, should be in the one-round equilibrium relative to the play function, where we would play, well, where we do the move in the current round, and then continue according to the strategy. So basically, this has only like one hole here, which is that move in the current round, and the future is just as prescribed by the strategy. So the current strategy has to be optimal with respect to this payoff function. And so this is like, I don't know, this is like just local optimality. And then, however, what we also need is that for all y primes, if I look at the later of the current thing, meaning if I look at all the things that I could reach by making some move, then the same condition has to hold again. The condition is this gamma with respect to a slightly modified payoff function. Namely, the payoff function is modified in that we now record that we had moved to y prime.
Yeah. So if I think about one deviation principle, I think about it's a method in economics to use induction. So how is that related?
Well,
So we do have co-induction here at this point.
I could maybe, I have an,
So one deviation is baked into. So you see this definition. For an equilibrium, the strategy to be in equilibrium for the infinite game, the strategy must be in equilibrium for the first shot, for some utility function, and then recursively for the second shot, the third shot, all those shots. So that's giving that's the one deviation principle. Why they formalized it using induction, I guess, because they don't make co-induction. And then
So maybe this point actually in this style.
I think it's a co-inductive principle.
yeah, so I wanted to mention, I mean, in principle, you can also,
But if you formalize it inductively, then you'll call it induction.
Yeah, yeah, yeah.
the thing is, if you have, shit.
I should say you can see the infinite as a completion of the finite rather than dual to the finite. And I assume that that's what people who study the infinite using induction are doing. Because it's not daft, it's just a bit oh hat.
It's not daft. Let's conclude like this. The point is, yes? The point is the following. If I look at the infinite streams, for example, you can also prove stuff about induction. You also can prove finality of that stream coalgebra. How do you prove it? Well, you can prove it by induction, in fact.
So then the interesting question is, could we prove something by co-induction which we cannot prove by induction? So
Can we ask
would
that
be-
question at the end of this talk?
Yeah.
That's quite right.
But related to this, co-induction is often just a more elegant method rather than one which is fundamentally increasing your power or something. Maybe. That could be, I mean, depending on the types you're reasoning about, I guess.
That would be bad, or say not bad, but
I mean, for the one deviation principle both, this is not something which falls from heaven, but we have to make substantial assumptions on it. These assumptions, I haven't seen them here. So for instance, continuity assumptions and so on. Is counting, which is one way of getting it.
Right. So I think it's good to have this mix of kind of things here. So in this setting, it's not something you have to require condition built in. But if you notice, however, that in the first stage you've got a particular utility function, and as you go to the further stage, that changes. So those assumptions, I think, are being discharged by more refined conditions. That could be the answer.
So we have to investigate that.
she's already writing the paper we wanted to write because that's exactly the question.
So let me make one remark which is basically underlying all my confusion at the moment, which is, so at the moment what we're doing here is we're taking this monotone operator on index predicate, which is basically, an index predicate looks like this. But now we do the magic of currying, right, gives us just something of this type, which means this is just a predicate then over pairs of this kind. And this is kind of related to what I'm going to say in the end, I think. Because if you take this view, then you're just basically in the world of predicates as you know them. And then you can show that the predicates that play a role here are invariant under bisimulation. Because I can't so nicely talk about this index predicate with respect to bisimulation. But if I have just this thing, then I know a lot about it. And yeah.
I guess the alternative we've still got index bisimulation.
Yes. Okay. So actually, I was about to show you anything of the proof, but I'm not going to really do. It's always kind of escaping. No, what I wanted to say is it's not a very difficult proof to show now that with these definitions in place, it's the final coalgebra. It's non-trivial, but it's not very difficult because you know what you have to prove. Eventually, you're going to prove it. So in order to see that this is now the final coalgebra, what we have to consider is some arbitrary open game which forms an FG coalgebra, which has this FG coalgebra structure. And if you know that you have this FG coalgebra structure, what you always have is this kind of two maps which correspond to like an automata structure and the stream coalgebra structure. And if we have such a thing, in order to show that this is final, we have to show that there must be a unique map from here to here, making this diagram commute. And so what's really obvious is that the uniqueness of this thing, because if you have such a morphism making this diagram commute, it has these two parts, and you can show that these are just coalgebra morphism for these set coalgebras. And we know that for the set coalgebras, these are final coalgebras, so that's why they have to be unique. And so the only slight difficulty here is that we have to prove that this thing here is in fact a morphism in, well, in this category of two opens. But I'm gonna spare you the details, to be honest, and especially myself. I mean, the details are all in the paper, and I'm happy to discuss them, but it's clear that it doesn't really help much to go through this now. So here I was yesterday briefly confused by saying, so where did we now, because I had this slide about A arrow is kind of subgame perfection in functorial form or something. And where did we ever use this, right? Because subgame perfection is introduced here in a way. So why is it also there? And the reason why it's also there is that, in particular, for that whole thing to be a final coalgebra, we need in particular that this is a coalgebra. And so therefore, the condition for this functorial construction on the equilibrium has to be in such a way so that it matches up with the actual equilibrium condition on this final coalgebra. So therefore, that's the point here somehow. So while the subgame perfection was really defined on the previous slide in a sense, we also needed the A arrow to contain the subgame perfection already, because this arrow has to be an arrow in this category of open games. Not this one, but now I'm confused briefly. No, of course, this has to be an arrow in the category of open games. So now briefly, I wanted to mention this. This is the main result of this talk. This is the final coalgebra. So now let's go back briefly whether we can do anything with this. And so I just have sketched here what we have in the paper, basically. So we have the iterated prisoner's dilemma. So what I'm trying to do now is to show you that a certain strategy is in fact subgame perfect, that we know should be subgame perfect from the classical literature. So I'm not trying to prove anything new, I'm just trying to reconstruct the result from the literature with our method. Okay, so if we, this is just a basic fact. For the iterated prisoner's dilemma, one way of getting a payoff for an infinite sequence of moves is just by taking the utility function for each round and start discounting it with some beta. So the beta should be ideally smaller than 1. Sorry. Yes, it's smaller than 1. And in any case, to make this sum somehow convergent. And this is a very standard way of doing payoffs. So the strategy we are considering in this game is just the following grim trigger strategy. So I told you in our construction it came out very naturally just from the fact that we needed the isomorphism, that strategies have to be some kind of automata. And so the grim trigger is now the following automaton. We start here in this cooperating state. Whenever the round that we're playing continues to cooperate, we stay in the cooperating state. If somebody deviates, we move to the defect state where we loop. Now, how are these different? Well, so this is not the full structure. This is just the transition structure. The output function is defined here. So if we are here, the output of this state is cooperating. It means as long as we are in this state, our strategy is to cooperate. As long as we're in this state, our strategy is to defect. And if somebody in this state doesn't stick to that strategy but deviates, we are just having hell breaking loose. And so our goal is just to show that this strategy represented by this automata state is an equilibrium. And again, I mean, I'm going to only sketch it very, very yes. Let me see how much of this notation we need in the second slide. And then probably, so how do we prove this? So what is this? We want to show that this is an equilibrium in the game we are given. So the equilibrium, remember, of the iterated game was defined as the greatest fixed point of a monotone operator. So in order to show that something is so we want to show that a strategy is an element of this greatest fixed point. In order to do this, we have to use general fixed point theory, and we have to provide somehow a predicate that is by itself a post-fixed point of the operator. Then we know that this predicate is contained in the fixed point. And we define this predicate in such a way such that the strategy we are interested in is an element of this predicate. So we define an index predicate of the right type for the prisoner's dilemma. And what does this index predicate do? Well, it takes the utility function, and then we just define it to be all the states that we can reach from the initial state we are interested in by reading an arbitrary word. However, so and for which then the K is the W derivative of the original payoff. Okay, let me backtrack. We need one definition. Remember, we have the payoff function of the prisoner's dilemma. What happens now is we are looking into what happens like after finitely many steps. Suppose we made n moves. We want to know what happens. To represent what happens, we have to do several things. So on the one hand, there's a way of updating the strategy, because we start with a strategy, then the game evolves, and somehow we update our automaton, and we come out at some other state. So this is the state xw. Forget how it is defined concretely. Xw is just kind of the strategy that we are having now after reading what happened until now. And kw is like, originally we started with a utility. Now we read some w. So what happens now is that we get the utility, we update the utility in the following way. The new utility is the one function that always prepends the w that already happened to what we get next. So that's the updated utility given the history until now. And so this predicate here, what does it do? It takes QC of W, so it's like the state that we reach from QC after reading W. But so it adds this state to those payoff functions that we get that corresponds also to reading W. So we kind of relate exactly the update of the payoff function. So in a way, you could see that as pairs of states with payoffs where we read the same word, that we updated using the same word W. And so the point is now just that, okay, clearly QC itself is an element of KIPD, because KIPD of the empty word is just KIPD, and QC of the empty word is just QC. So QC, the strategy which we're interested in, is an element of that index predicate for our utility for the iterated prisoner's dilemma. So trivially, we know that the strategy we're interested in is contained in here if we can show that this predicate is contained in the equilibrium predicate we are done. And so for this, we show that it's a post-fixed point operator. And to show that this is a post-fixed point operator, technically that means that we have to show that chi of k, if we apply phi to this chi, we get that chi of k is a subset of phi applied to chi of k. That's just the definition of what it means. And then we just have to prove this for all the k's. And so the lemma we have that this works basically if beta is bigger or equal than 1/3.
So, because you've got chi as an indexed predicate,
Yes?
the natural order is pointwise, and hence you get this sort of for every k this thing so. But if you switch to what you did over there,
Yeah.
just use a predicate, then is it the case that you wouldn't be using for every k, you wouldn't get this format, you get a different answer. Take the predicate approach, build a monotone operator, look for a postfixed point, it'll be a different formula.
Right, we don't get every k here. Similar to we get all the k's. So the picture here, if you would switch to this thing here, is that you start with some x, c, and some k.
Yeah, exactly.
And then you have a coalgebra structure, basically. And you just generate anything that you can reach inside this coalgebra from this initial state. But the k is still there.
Right, but would you get the same theorem?
The same theorem.
The same theorem, which is worrying me.
So that theorem is only interested in, I mean, basically the theorem is trivial basically for the k's that are not of this form. I mean, while we kind of quantify over all k's, as far as chi of k is empty for those k's which are not of this shape.
Yeah.
And therefore,
So you're sure so you think you will get the same theorem?
I'm quite sure, yes. So I have now some slides here which, however, are very technical, so I'm not going to do it. I can talk you through it over, I don't know, lunch, probably not, rather beer, I think. But, okay, so this is the proof of the lemma. We have it in the paper, it's detailed. It really just proves that thing, and the discount factor beta bigger or equal than 1/3. The thing is, we started with a payoff function for the prisoner's dilemma, which was already in some papers, such that we also were sure that this is the correct beta. So, blah, blah, blah. Yeah, and this is the 2 slides of experimental stuff. There's not so much, but just to make this more formal, what I just told to Neil here is that we have both this update of the state of the strategy and the update to the payoff. What we can do is we can kind of define a different coalgebra of what we saw so far. It takes together the states of the strategy and the payoffs. And now what does this do? Okay, we start in a state and the payoff. And then in each state, we just say, okay, this is our strategy now. But if something happens, we update our strategy. And then we also update the payoff according to what happened right now. And so the second condition here is the thing. The second condition, sorry. This should be on a different slide. Yes.
Can you wrap up and then we move to a discussion session and then you can keep talking in the discussion session?
Okay, I have just one more slide, so that's easy. Hopefully that's less. So the point is now here what we can do on this coalgebra, we can just define this predicate in some kind of logical way. So we had this, or whatever you want to. I mean, I'm not religious about it, but I am in fact. So basically what you can do now is you have a coalgebra structure, and you remember that equilibrium condition had these 2 parts. One was the local condition, and the other one was what happens in the next state. And so now you can define some kind of easy, very simple predicate, which is like exactly checking this one-step condition. This is this one here. And now if you define this, so basically this just says, in my state currently, the strategy that I'm about to take according to the strategy is in fact an equilibrium for a properly updated payoff function. Properly updated means just that here we kind of say, we assume basically that the future continues according to the strategy. We say, this is like what happened when I mentioned this phi operator, that was there as well. And so the proposition now is just that if I take such a pair and I take this kind of formula in the mu calculus which just says nu x, box x, and this condition, that really just ensures that this should be hold true everywhere where I can go, then x is a subgame perfect equilibrium for the iterated game with this payoff. So what did we gain with this view? So first of all, I think eventually we will gain, even if we don't go for the logic, eventually we gain something from this view, to be honest. At least it will give us more insights. Okay. But the other thing is, you can easily argue why this predicate here is invariant under bisimulation for the functor we're talking about. This formula is invariant under bisimulation. So that means that now in order to check this, what we are allowed to do is, in this coalgebra here, we are allowed to identify bisimilar states. And so while that thing here, that coalgebra which I just defined, is of course wildly infinite, if we just start in the particular state, we also know that these control states, so to speak, are just a finite set. If we can say something about why certain payoffs leads to the same one-step equilibria, then we can reduce this to very few states. And so the idea is the following. Although while walking here, I realized that there's already something slightly wrong, but only slightly. So the idea is just that in these iterated games that work like the prisoner's dilemma, so on the one hand, the payoff should be computed as in a way similar to discounting. And also the one-step equilibrium should be similar to the argmax. That's what I forgot here. I think we need something like this. We need to check this condition only for states of the form xk, where x is an element of this automaton, and k is the payoff function of the prisoner's dilemma. So I think for the prisoner's dilemma, we would have to check only two pairs, xc with the payoff of the prisoner's dilemma, and xd with the payoff of the prisoner's dilemma. Because updating that payoff with the history, so to speak, doesn't really change the one-step equilibria, because it's just a constant factor corresponding to the history so far, which is totally irrelevant for the current equilibrium. So therefore, yeah, that looks quite efficient for checking equilibria, because the problem here is that this strategy is very basic. But in general, if we just have an automaton, we just have to check for every state together with the payoff, the initial payoff, whether this is an equilibrium. The now x is an equilibrium of that blob. Okay, that's it. Thanks.
So we have 20 minutes of discussion session officially. So let's roll questions into the discussion session. Yes.
So even if this iterated game has obviously the A or the Y get very recorded. The one that coded previous moves. And then you said that you have that, but you also have the state X, which is trivial. Now intuitively, the history, so the previous moves should be the states. No? No?
No.
Why not?
So this is
Go ahead if you want.